Welcome back to the series where we make Wi-Fi simple and fun. Are you curious about how Wi-Fi knows when to talk and when to listen? Today we're going to dive deep into the fascinating world of medium access in Wi-Fi. We'll break down the complex concepts like CSMA, CD, virtual and physical carrier sense, and more in the way that is easy to grasp. By the end of this video, I promise you'll have a solid understanding of how Wi-Fi manages to keep all our devices connected seamlessly by taking turns and talking. Wi-Fi devices share the same medium, which is RF in this case. So how do you access them and who accesses them? So CS here stands for carrier sense, which means can I sense if anybody's talking on that medium, yes or no, and then medium access. After that I can get the access to the medium. Now in Ethernet I can detect the collision, that's why you have collision detect. But in Wi-Fi I have no way of detecting a collision, so I use collision avoidance, which means I'm going to try and avoid that collision at every cost. So not speaking over anybody else is pretty much what an avoidance in this case means. Most important thing to realize here is if I send something and I haven't got an acknowledgement back, I assume that it had a collision and I have to retransmit that frame. Now best way to imagine this is, let's say we are four friends standing together and trying to talk. Now only one person talks at a time, we know that, right? But who else is gonna talk? Or I must say, who should be talking at this point? One of us, right? And the other two people or other three people should make sure that I'm not gonna talk over that person. So we have built these communications ways of avoiding that conflict. Is what happens if I talk over somebody? If I talk over somebody, nobody will understand what anybody said and I'll have to repeat that same thing again. So there was a collision there, we have to retransmit. That's pretty much what it is. So we can detect a collision in case of an Ethernet, but in Wi-Fi, I rely on acknowledgements. If I don't get an acknowledgement back, I assume that the communication had some sort of collision and I have to retransmit that frame again. So that's a very important concept that comes with Wi-Fi. Now, collision is not a good thing. How do I avoid as a human is I make sure that nobody else is talking at that time. When everybody is kind of quiet, that's what I find a chance and I start talking what I have to say. Or I'll take pauses to make sure if the other person in front of me is about to say something or not. So these are some of the things that we do as humans to avoid the collision. Now Wi-Fi is very similar. So let's look at some of the methodologies or some of the ways that Wi-Fi has developed in its standard to avoid these collisions, because as we already know that these are not good, so we have to try and avoid them at every cost. So let's see what they are. Now the 802.11 standard defines distributed coordinated function DCF as a process devices must follow in order to share access to the medium. Now this process is used in each standard since the original standard in 1997 was discovered or came out. So the four things they really came up with this is the physical carrier sense, the virtual carrier sense, random back-off timer, and the interframe space. And obviously going forward in all the slides, we'll discuss each one of them. But important thing to remember is these are the four things that you have. You have the physical carrier sense again, the virtual carrier sense, pseudo-random backup timer, and the interframe space. The Wi-Fi world, we call this clear channel assessment, where I'm trying to make sure that the channel is clear before I start talking. Now again, both the virtual and the physical carrier sense are always happening at the same time. Let's see what they are. Now physical carrier sense is simply trying to listen to the channel to see if anybody else is talking or no. As I said before, our humans, we do the same thing to avoid talking over somebody else. So physical carrier sense, I'm just going to look for that silence. The medium is silent, nobody's transmitting. That's my chance to speak now. This way I know I'm not going to speak over anybody. That's the idea. Now again, you also have to understand that Wi-Fi works in a frequency that has other technologies also. So it's not just I'm going to not avoid Wi-Fi transmission, but also something else that's transmitting on the same. That is also the reason why we have the two options here that you see, which is signal detect and the energy detect. The signal detect is pretty much threshold, or simply put, my way of making sure that I'm not speaking over any Wi-Fi signal. Now energy detect is somewhere where there is something else in the same vicinity, like a cordless phone, a garage door opener speaking at the same time. Now signal detect, the threshold is 4 dB signal to noise ratio. Now noise ratio, generally speaking, is about 90 dB. Now if I'm getting a signal up to 86, that means a very weak signal could also disrupt me from speaking up. So that's why Wi-Fi is a very polite protocol as you might see it. Now energy detect, the same is 20 dB above. So it was 86, I will try to defer, but in this case 66, I will defer. So that's the whole calculation for signal detect and energy detect. The main thing to remember, as I said before, signal detect is for Wi-Fi, energy detect is basically for any non-Wi-Fi working on the same frequency. Now the next one is a virtual carrier sense. If you remember in the previous videos, we spoke about in the actual header, it has something called as duration field, which really means is how long this frame is going to take to transmit. So obviously if I'm going to say that, okay, by the way, I'm going to be talking for the next 10 minutes, anybody listening to that knows that, okay, there's no point trying to look for any scope because this medium is going to be busy for next 10 minutes. So they set up a timer. That timer is called as nav timer. So in this particular slide, if you look, it's showing that it is 44 microseconds that I'm going to take. And then I'm going to set up my nav timer, which is network allocation vector time, which means that, okay, this is how long it's going to take. So I reverse count it until I get a 0. So now I'm going to start checking again if anybody is talking or no, because that 10 minutes already booked. After 10 minutes, then I'm again going to look to see if anybody else is talking or no. So that's pretty much the concept behind this duration field and the nav timer. Now the next slide, let's look at the actual nav timer in action. So this is just a visual representation, and this one is basically exactly what I said before. It's using that nav timer, right? So it's setting up that time to that nav timer, and before the station can actually go ahead and transmit, it's going to make sure that the nav timer is down to 0 before it can contend for the medium again. Obviously, as I said before, 10 minutes, we know for a fact this person is going to talk for 10 minutes. So no point looking for 10 minutes. I count in the countdown way, and once the 10 minutes are up, look for the medium again to see if it's available. If it's available, then you go for it again. All this has been done just to make sure that we don't talk over each other. Now this example, another interesting one. So in this case, the station 1 is the 44 microsecond. Everybody else have set up their nav timers to 44 microseconds, which is saying, okay, I'm going to wait for 44 microseconds. I'm going to count down the 44 microseconds because I know the station 1 is going to be talking during that time. That's exactly what this diagram is trying to show you. Now think of this like a flow chart, right? So device has a frame. I want to talk about something. I want to say something. So first of all, obviously, because there are a few people who want to say something, we all use a random backup timer to wait. And then we go through that clear channel assessment. We look at the signal detect, the energy detect, which are the two ways of physical, making sure that nobody's talking. And then I kind of go back based on that timer. So this is again a flow chart which tells me that what's my flow before I can start or begin to transmit. The whole system is built in such a way that we are trying to avoid collision at every cost. The reason we're doing that is because in Wi-Fi, I have no way of figuring out that if my frame had a collision. The only way I have is an acknowledgement. If it comes back, then I know that my frame was sent properly. If I don't, then we go off, right? Now, let's look at the random back-off timer here. Now, at this point, I've made sure that the clear channel assessment has been done. I have taken a pause, which is the diff, interframe space interval. And then I'm going to just come up with a random. Think about this. Remember, initially I said we were 4 friends trying to talk. Now, let's say at this point, nobody was talking. So who should go first? All 4 of them roll their dices. Depending on what number you get, you start counting in reverse. Once you get to 0, you again take a pause to make sure nobody else is talking, and then you go for it. And now at this point, the first person goes for it. The others kind of listen to that, say, okay, yeah, somebody started to talk. Then they stop their nav timers, stop their back off timers right there. And then they start all over again. Now, just to keep it simple, there were 4 people. Let's say they all picked up number 1, 2, 3, and 4 respectively. So the number 1 guy counted 1, 0, he's done, he can transmit. At that point, when he counted 1, the others were already counted. So the number 2 guy was on 1 second, number 3 guy was on 2 seconds because now 1 second is up. So they don't have to select the random backup timer again. They just pause that to what time they waited. So that when the first person is done transmitting, they compete again among these 3, and now the number 2 will be able to go because his number was 2. And this is how the numbers have been picked up. And again, the slots are picked up between 0 to 15. But depending on what kind of technology you're going to be using, like OFDM in this case, so you're going to be waiting 9 microseconds for per slot. So if you pick up 4 slots, you multiply 4 into 9 microseconds, which is 36 microseconds is going to be your back off timer in this case, right? So that's just an example of exactly the same thing that we're going to pick up. So 3 stations picking up random. In this case, obviously, you know that the station 3 is going to go first because his number is going to be the shortest. The number that you pick up is between 0 and 15. Now think about this. If they were the 4 friends and they had just 1 dice, so the chances are the maximum number you're going to pick up is 6. So the maximum seconds you wait is, let's say, 6 seconds. But now if I tell you that you're going to use 2 dices, now you can go up to 12. If I use 3 dices, you can go up to 18. Similar concept we have in Wi-Fi. Start to transmit and you get a failure which doesn't go through, no acknowledgement. So that's a retry now. Now you're going to try and pick up because you'll say, you know what, the medium is busy. So let's pick up a bigger number. So instead of picking from 0 to 15, I pick up 0 to 31. Every retry, you see the number is going up 0 to 63, 0 to 127, and so on. That means for my Wi-Fi is a client could have to wait really long. If you have to wait really long, that means it will take really long for it to transmit. So it's going to be a problem. It will have a bad user experience when I'm trying to make that call, right? So that's where the challenge is. So that's why too many retries are not good. You will always have retries in your network, but if you have a certain percentage and there are too many, then that's a little bit of a problem. And in case you don't forget, you always get a retry when you don't get that unicast frame acknowledged back. So if I send something, I don't hear an acknowledgement back, I have to retry. So the more retries I have, the longer wait times I could get. Now this is very similar to us too, right? When I'm talking on the phone with somebody, if I don't hear anything back and I'm talking for next, say, 30 seconds, I have a tendency, I'll say hello, just to make sure that there is a person on the other line who is able to hear me. Then we have the interframe spaces, which were equivalent to pauses. Now in this one, to be very honest, there are a few of them, but the main one is the SIF, which is a short interframe space. In today's world, I would say, if you're using DCF, you have the diff, which has low priority, and then you have the AIFS, which is the arbitration interframe space that is dependent on the QoS, in which simply I'm just trying to prioritize voice application because voice applications are time sensitive. So I'm going to take short pauses instead of taking long pauses. So think of them as different kind of pauses. In some cases, I take long pauses. In some cases, I take short pauses. That's pretty much what these are. This is pretty much like when I'm sending data, I take a pause, then the acknowledgement comes. Again a pause, then more data comes. So it's almost like I'm trying to make sure I'm pausing. And again, in human interaction, we do that a lot too. I want to just make sure that, is that person in front of me trying to say something? That's all I'm trying to avoid. Now let's look at in human world how this whole system works. So as I said that an example of those 4 friends, they're almost like in their head, they're saying, is anybody talking? No. Maybe I should wait a while just to make sure anybody else doesn't want to say something. If they're still quiet, then I think I can talk. Then you talk. Did they hear me? Did they get an acknowledgement? If not, I'll have to say it again. That is exactly how we humans talk, and that is exactly how a Wi-Fi system would work. So this is a very good description of how Wi-Fi contention really works. So the DCF components made up of 4 things again. The carrier sense, which includes the physical and the virtual carrier sense. Physical carrier sense again divided into the energy detect and the signal detect part. Then you have the interframe spaces, those are your pauses. The back off timers where you try to figure out who rolls the dice and who gets what. And that's pretty much what it is. These 4 components are the 4 pillars of trying to make sure there are going to be no collisions. Does that mean they never happen? Well, obviously they do. How do I know it happened? I did not get an acknowledgement back. So at this point, I am really hopeful that this concept has been nailed into your head because I've said it a few times. So now let's move on and see what's next. Now the next really is the hybrid coordinated function. Now HCF is method used in Wi-Fi to manage how data is sent over the network, similar to DCF, but it's just a little more advanced. It has 2 types. It has EDCA, which is enhanced distributed channel access. This method, think of this as it gives different priorities to different types of data, like making sure video calls or voice calls get a priority and they don't have to wait very long. Terms are frame burst and transmit opportunity in the previous slide. Now this is again expanding on that EDCA. You're seeing they had 4 different buckets. It has the background, the best effort, the video and the voice which gets the highest priority. So again, I'm trying to give priority to certain kind of traffic to make sure that goes smoothly. This is similar to those 802.1d tags, which is again QoS on the wired side of things, to make sure that that priority goes, because the QoS has to be end to end. It doesn't make sense if I try to prioritize something on the Wi-Fi, but I haven't tried to prioritize that traffic at the back on the wired system, which obviously every AP is connected to a wired system. So it just makes sure that the priority is end to end from this perspective. Visually, see 4 buckets, every bucket gets something. The 2 buckets which are low priority will get full at some point, the best effort in the background, but the voice and video, nothing will stop, it will keep going. Again, the next transmit opportunity, which means the next time I'm able to talk, I make sure I empty the voice and the video buckets first. And once they're empty, then I will work through the best effort in the background buckets. That's pretty much what you need to understand from a priority perspective. And again, if you look at the top of the picture, 802.1d is where the wired are. That's where I'm making sure that it's been prioritized at the back also. Okay, so that is QoS in action, trying to prioritize. Now, initially when DCF came on, another option that came on was PCF, but PCF was not adopted, so DCF got adopted. Now, this is similar to that, but it's a little different. It's basically built into the AP, which is trying to make sure that I'm giving everybody a transmit opportunity. So instead of everybody able to have that roll of dice, AP will decide who can talk now. Think of that as one person who's an instructor in the class. He's telling the students, okay, student 1, you go, student 2, now you go, student 3, now you go, something like that. Block acknowledgement, which just means that instead of acknowledging each and every frame, I can block a bunch of frames. Instead of say you send me something, I say I got it. You send me something again, I say I got that too. You send me something, I say I got that too. So instead of say, okay, I got all 3 of them. So that's pretty much the block acknowledgement. Again, efficiency has been driven by doing this. And again, it can be of 2 types. I could have immediate block acknowledgement and the delay block acknowledgement. So depending on what I'm trying to do, I have 2 kinds. This is again a visual representation of showing that I got all the data. So I had QoS data 1, 2, and I had CIFs in between. I'm taking those pauses, but I'm acknowledging, instead of sending acknowledge after everyone, I'm saying I got all 3 that I explained before. So that is pretty much block acknowledgement from a perspective. In this case, obviously the AP was sending and the block acknowledgement required was asked, and then the recipient said everything received, all 3 received. Now this was introduced by Wi-Fi Alliance, which is the WMM thing. It is again the QoS. It is a feature that helps different type of traffic, voice, browsing, to make sure that something which is more important gets priority. By setting up priority levels, it has 4 access categories that we saw before, and it's also matched to the 802.1d tags. So the tags that you see on this side, that is exactly that happens on the wired side. So again, as I said, it's trying to make sure that you have QoS end to end. That is the whole purpose of this. Now, how does it achieve it on Wi-Fi? Is by giving the smaller numbers. So voice, because I want to prioritize, you only pick up a number between 0 and 3. Now the chances are you're going to pick up between those 2, rather 3, and you'll go first as compared to somebody who's a background. But think about this. This is still a probability. There is still a chance that a background could pick up a 1 versus a voice could pick up a 3. So the background could still go before the voice. But again, the probability is that the voice will go first. So again, it is not definitive. It's a kind of a probability based QoS system in Wi-Fi, because I still be able to pick up a different number. Last thing I want to talk about is the airtime fairness. What does this really mean? Now think about this. You have a bridge. Only one vehicle goes at a time. Now you have some cars, the small cars that go much faster, but then you have a big truck too that takes a long time to go. Now you have a line of cars waiting and you have a line of trucks waiting. Now does it make sense to be fair that, okay, we send one car which takes, let's say, 1 second, and then we send a truck that takes 5 seconds to cross? How would I do this? I send 4 cars in 4 seconds, and then I send a truck. So now I'm kind of matching that. So this diagram that you see here is trying to depict the exact same thing. So the first option is when I'm sending it kind of, one by one. Now this, what happens is at the end, all the 8 cars and the 8 trucks are waiting. And now, but if I use the airtime fairness, By the time the third truck comes, all the cars that were waiting are already gone. So no small traffic is waiting. Now don't forget, what's the small traffic in this case? Usually the voice packets. So you want them to go fast. So this is what the airtime fairness is. It's trying to be fair, saying that, okay, if you're fast, okay, I'm gonna have few of you go first instead of all of you go at the, one by one kind of thing. So that is the whole idea of airtime fairness. And that wraps up our deep dive into the medium access of Wi-Fi. I hope you found this breakdown exciting, as informative as I did. If you enjoyed this video, feel free to leave your feedback and let me know what you liked versus something that you did not. Until next time, bye for now.